Okay, we will go ahead and get started. Before I begin, I just want to make sure that everybody can hear me okay and can see my screen.
Yes, we can.
Okay, great.
Yep.
Yep.
Great. Always want to make sure that the technical part works as well. So we'll go ahead and get started. And just wanted to thank you for joining in with for our this month's webinar series on Pigments 101. Today we will review the quinacridone pigment chemistry. And just a few housekeeping items. We will, this will be about a 35 minute technical discussion, and we will provide some time at the end for any questions and answers that you might have along the way. If you do have questions, please feel free to use the chat box, and we will address them at the end. Like our past webinars, this will be recorded, and we'll send out the link to the recording as well as the PDF of the presentation to all the attendees after we conclude this session. So, and there we go. You know, with all of our Zooming here, I'm finding it more and more important to infuse a little humor in everything we do. Hopefully everything is okay with my camera on here so that we can have a good learning session here. So as the name implies, we are starting with talking about quinacridone pigments. And there is a lot of knowledge and history of this class of pigments that is available. Especially for the main pigment, the quinacridone chemistry, all of its substituted derivatives, their polymorphism, and then their solid solutions and isomers of this particular chemistry. So it's a very well-known chemistry. This family of pigments ranges in color from golden yellow to scarlet to maroon and red and to magenta, and finally on the very blue side, the violet space. However, the more commercially viable products are in the maroon, red, magenta, and violet color spaces. Quinacridones are extremely useful in all application areas, primarily because of their outstanding chemical and photochemical stability. They also have very low solubility, and they also provide some attractive colors to your formulations. The quinacridones fall in the polycyclic class of organic pigments. So you can follow the trail of these. And then more specifically, you can see where the quinacridone lies with regards to the polycyclic organic pigments, and they are also part of considered a high performance pigment. So we've seen this chart before. Again, it's really just a reconfirmation of the differences between a high performance pigment and a classical pigment in terms of their technical performances. The high performance pigments provide you the light and weather fastness that's required if you have an exterior application. It also provides a nice heat stability or heat resistance if your application requires a high temperature for curing or dispersion processes. And they are also very good with respect to fastness to solvents. in there. Unfortunately, they do come with a higher price than the classical pigment, but there is more than one way to look at the price of a pigment. The high performance pigments, we tend to address them more for their value that they bring to you as a colorant versus just the dollar per pound. So that the true cost of the raw material that you're using is in context of the total formulation, is that cost and use. And you've probably heard this phrase used in the past, but when you take into consideration both the technical performance properties as well as the color that it brings that value in use to a higher level over a classical pigment. Quinacridones were first synthesized in 1935. However, it was in 1955 that DuPont established some new synthesis methods that make them more viable for commercial production processes. They've also identified the polymorphism that exists and established their photochemical stability properties. In 1958, they were able to isolate and identify the two crystal structures for commercializations of the violet 19s. Then there are three major chemical constitutions of the quinacridone backbone: the unsubstituted quinacridone, which is your violet 19, the 2,9-dichloro substituted quinacridone, that is going to be your pigment red 202s and pigment red 209, and your 2,9-dimethyl substituted quinacridone, which is going to be your pigment red 122. And those are the three main chemical substitutions that are commercially available for the quinacridone chemistry. And then also quinacridones can also be further modified and used for solid solutions to create additional color indexes and options for your colorant needs. As we noted, that the most notable properties of the quinacridone chemistry are their outstanding stability performances, both the chemical and photochemically, and their very low solubility. So they are very stable to a wide variety of solvents and resin systems, depending on what your needs are. And of course, they do provide some very attractive colors too. Their uses are in all application areas, but because of their fastness properties, they play a heavy part in exterior uses where that exterior durability is required, like automotive types of paint systems. They also bring a measure of higher tint strength to your formulation, so that you can take advantage of that value and use less pounds in your formulation and still get the same types of color that you need, along with the superior technical performances. Of course, these are also used in high quality printing areas where you want those more unique color properties, but also if you have an exterior need as well. And the high heat resistance makes it a very popular colorant for coloring plastics, especially engineered polymers where the temperatures are much greater. So as I mentioned, the most commercially acceptable pigments are in the more red, yellow shade red to the red shade violet area. The pigment red 202 color index will be your most yellow shade, and then the reverse, the violet 19 beta crystal will be your most blue shade red, and then the 209, the violet 19 gamma crystal, and the red 122 fall in between there. For Sudarshan, we offer products in the pigment red 122 and the violet 19 space. Both crystal structures are available from Sudarshan. So we talked about polymorphism in a few other webinars that we've had before, and to refresh your memory, polymorphism is a method where the individual molecules of the chemistry come together in a crystal structure that is unique to that particular crystal structure in there. So with violet 19, there are two structures: the gamma modification, which results in the more yellow shade of that one. Still carries the same technical properties and very nice shade as well, but the crystal structure of this brings it to the yellow side. The other one that we talked about is the beta modification, and in this particular case, the combination of the molecules to form the crystal results in that very blue shade red to near violet. And that's especially noticeable when you bring it to the tin tone shades, where you can see the more yellow and the more blue shading of these two different crystals. To give you a little bit more of a flavor of that polymorphism, and here, so we've got the way the gamma crystal of the violet 19 is put together is the more complicated of the two crystal structures. Here, every molecule of the violet 19 quinacridone is connected to 4 other molecules, so it's very complicated. So you can imagine when you bring the full structure together, how very complicated the structure can be to be able to create that nice yellow shade red color space. From Sudarshan perspective, we offer a number of products in all of the areas of application areas, and a number of choices within those application areas. But I know I've said this in previous webinars, just because we have them in a certain application bucket does not necessarily mean that a product won't work in another application. These are placed in the buckets primarily by the finishing techniques that are used for that general type of application in there. But it's not to say that for example, the 2988C would not necessarily work in an ink application, for example. But it's just a way to identify how the finishing techniques are done by placing them in these application buckets. And then similarly with the beta crystal for the violet 19, this is the more simple of the two crystal structures, where each individual molecule is only connected to 2 other molecules in that crystal shape. So the actual crystal itself, the structure is much more simple and provides that blue shade and more transparent types of a pigment in the end application. And similarly, we offer some products in the beta modification as well. Similar comments here that we've placed them in these application buckets by the measure of their finishing techniques, but it's not to say that they can't be used in others. So when you leave the base structure of the quinacridone pigment violet 19 and you start to grow and add constituents onto the to the spaces on that structure, you start to create the derivatives. And if you start with the
you were frozen there for a minute. Can you back up a couple minutes?
Oh, sure.
Or the beginning of the slide?
Yeah. Okay, so I'll start with this slide. Is that okay? I apologize.
Yes.
Okay. So we're in the we're talking about the derivatives of the violet 19 backbone. And so if we start with the violet 19 and we add a methyl groups to the number 2 space and the number 9 space, that will create the pigment red 122, which is a nice magenta color. And now if we change that number 2 and number 9 position to hold a chlorine, then we get the pigment red 202, which is a nice red in color. And if we stick with the chlorine, but then move that positioning to the number 4 and number 11 position, we create the pigment red 209, which is a more maroon type in shade for that one. So depending on what constituent you place and where you place it, that is how you generate the derivatives for these quinacridones. Just a little bit more about the pigment red 122. As stated, it's created by putting the methyl groups on the number 2 and number 9 position. It provides a nice saturated magenta shade. It does carry very nice light and light fastness and weather fastness with very good migration fastness and heat stability for plastics. So you can see where the color position is in the full tone, and in the tint tone provides a nice magenta color with that blue shade when it's let down with TiO2. The Sudarshan portfolio of pigment red 122s is very broad. So there are a number of options in each of the application areas. So there is something there that will meet all your needs in that respect. And then moving on to the pigment red 202. This one is using the same positioning as the pigment red 122. However, we've moved from the methyl groups to the chlorine groups in that number 2 and number 9 positioning, and that results in a nice saturated red pigment that is more to the yellow side than the pigment red 122. It does carry the same high properties as a typical quinacridone. And then, as we stated, if we move the positioning of those chlorines to the number 4 and number 11 spot, we create the pigment red 209, which then moves the color positioning. Even though the chemical constituents are the same, the positioning then moves it to a little bit to the more blue side. And so bringing those two together, you can see how the specific position of those chlorine entities all impact the final color positioning, especially in the tint tone colors. You can see where the 209 is much more bluer shade than the 202. So quinacridones are heavily used to create solid solutions, which then allows for some unique color positionings and the establishment of some unique color indexes as well. There are two types of solid solutions. The first type is bringing a host compound and one or more guest compounds together. And this is the more predominant version of the solid solution. And if you were to look at these products from an analytical perspective, the structure and the X-ray diffraction pattern will take on the form of the host compound. And so it is not as unique from an analytical perspective as it would be from a practical in-use application based on the color and the dispersibility of these products. The second type is where two or more related compounds are brought together in that solid solution. And here, these types will generate a new structure and will have a unique diffraction pattern as well. So from an analytical perspective, it will look different in addition to its application differences. And I've got examples of both of these two types. So the first type of solid solution is Pigment Red 206. This is a solid solution of the quinacridone molecule and the QAQ molecule in a 2-to-1 ratio. In that solution, that solid solution then results in the Pigment Red 206, which is a maroon, light fast maroon pigment that is described here. The QAQ molecule by itself is a very non-interesting or non-useful, I should say, pigment, because it comes with it some very poor light fastness and other properties, but it does bring a very nice yellow color to it. So the combination in solid solution with the quinacridone overcomes the issues with the light fastness properties by bringing to it the quinacridone good light fastness properties. The interesting thing to note here is when you are looking at the Pigment Red 206, it's in the general category of quinacridone pigments. It's got a unique color index name, the Pigment Red 206. However, if you look at the color index number, it's always going to have both the both parents, if you will, both the constituents of that solid solution represented in the color index number. So in this case, the color index number 7390 is the quinacridone, the violet 19, and the 73920 is the number for the QAQ pigment in there. So you're always going to see two if you look at the color index number. Now, if we take these same two ingredients, the quinacridone and the quinacridone and the QAQ, but flip-flop the molar ratios from 2-to-1 to 1-to-2, then we create the Pigment Orange 48, which is a very nice gold, the red gold type of an orange pigment. So similar composition, using the same ingredients, but just changing the molar ratio, we generate a new solid solution in color index name Pigment Orange 48. And so similarly, it does carry the unique name Pigment Orange 48, but it's got the two different color index numbers associated with it. And since it's the same ingredients as used in the Pigment Red 206, you'll see that it has the same color index numbers associated with it, just in a different ratio. The second type of solid solutions that I mentioned earlier results in the Pigment Red 207. Here we are combining the quinacridone, the violet 19, and the Pigment Red 209 that we discussed earlier in a molar ratio of 2:1. And here you can see that it also carries the similar naming context as before. However, the second item in there is the Pigment Red 209 in here. So I just also provided a little guidance on, from a color perspective, how these come together. You can see the quinacridone, the violet 19 mixed with the Pigment Red 209 provides that nice maroon with a pinker shade in the tint tone. From a crystal shape, the quinacridones typically fall in that needle type of a crystal. And here's some TEMs to demonstrate that. This is the gamma crystal of the violet 19. So you can see how many of these crystals are very long and very narrow in their structure. In this particular case, this product also has a number of shorter ones, but still the width of these are very narrow. And from the Pigment Red 122 space, here are two examples that also show how needle-like these crystals end up with the finishing. When we talked about synthesis of pigments, I've said it before, and you've seen this chart before, where the first manufacturing steps are used to identify the chemical identity or the chemistry of the pigments, and then once that end product is developed, then the finishing steps are added to provide the end use properties. With respect to quinacridones, that chemistry, there are two main process steps or processes that are used to create the quinacridone chemistries. The first one is termed the thermal or solvent process that was originally developed by DuPont in the 1955-58 timeframe. And the second one is the polyphosphoric acid or PPA process, which is a more widely used type of a process. Each of these processes differ significantly from the other, but they both share the key starting raw material, which is the DMSS in there. So a brief look at how the two different processes are done. Both of them are done in a one-pot process, if you will, for the three main synthesis types of steps. As I mentioned, the first step in the synthesis is to synthesize and isolate the DMSS. Once that's completed, the thermal process then begins with a condensation with primary aromatic amines. And that step is where the thermal gets its name, because it's a very high temperature step where the temperature is in the range of 250 to 300 degrees Celsius. And this also has a very high solvent demand for its process. And then the final synthesis step is the actual cyclization of the molecule itself to create that unique quinacridone process. And then the manufacturing continues on with the final oxidation, the pigmentation, and of course the filtration and drying aspects of it. The PPA process is also typically a one-pot process. The first step is, again, the same with the synthesis and isolation of the DMSS. However, the second step is where the PPA process is created, where the DMSS is acid catalyzed with aromatic amines. And then the third step of the synthesis is where the cyclization is done in also done in the PPA. The PPA process is a much more mild process in terms of temperature, typically in the 120 to 140 degrees C. The other thing that makes it a little bit more unique in process is that the drowning solvents that are used are typically tied to the end product that you're trying to develop. And so you'll see that in a little bit, the examples of that one. So this is a more chemistry specific process by use of that drowning solvent. So we talked about some key process parameters with regards to quinacridone manufacture, and to generate the crystal structures of the violet 19s is determined by what type of solvent is used in the drowning process. So to create the gamma crystal, water is used in that drowning process, followed by the polar solvent used for the pigmentation. Conversely, if you're trying to develop the beta crystal, then a solvent is used in that drowning process, and then followed by the polar solvent pigmentation. Pigment Red 122 also uses a water in the drowning process. From a key raw material and intermediate perspective, we talked about the key starting raw material of the DMSS. A key thing to note here is that there is a maximum yield of about 80% of this particular material, regardless of which process is used. And there have been many attempts. I know Sudarshan always is working at this as well, at improving this yield. But to date, the efforts haven't shown us to be effective, as we are always looking at ways to improve the economics of these types of processes. So that, of course, then leaves about 20% material that are deemed byproducts or that need to be eliminated and minimized. So this is done during that separation stage of the first synthesis part, so that going into that second stage of synthesis is a very clean and pure DMSS to be able to create this starting process for the quinacridone manufacture. So this is a chart that we've used in each of these webinars, and I've always had the little asterisk at the bottom with respect to quinacridones, because this one is opposite of what we've said before for other pigments. So if you are first time seeing this, this is great. But if you are trying to compare this chart to previous charts and other webinars, note that I've switched the order, the larger and the smaller in this particular areas because it is different for quinacridones. So in this case, I'm going to X out the other color area so you're not confused. But in your dispersion process, if you want to move the color of your pigment to a yellower shade red, then you want to lessen the intensity of your dispersion process. And conversely, if you want to move it to the bluer side, you want it to intensify your dispersion process. And similarly for on the violet side, to move it redder, you want to lessen the intensity of the dispersion process and increase the intensity of the dispersion process to make it go up to the bluer side. So with all high performance pigments, it is important that you get the most value out of that pound of pigment that you're using in your formulation. So your dispersion process has to be as optimal as possible. So to making sure that your pigments are well wetted prior to the dispersion process, that the full size reduction is made to the end result that you're looking for. And then once it's there, that dispersion is then stable so that you enjoy all of the value that you get from that pigment. Too often do we see that some of these areas aren't necessarily optimized, and you don't necessarily get the most that you can out of each of the pigments that you have in your systems. From a physical property area, I just wanted to show a few comparisons because we talked about how well the quinacridone family of pigments is with respect to light stability and weather stability. This is a chart that just is a comparison in a plastics situation that compares the different color indexes in a mixture with white with respect to light stability and how many days it takes before there's a noticeable fade in color. So you can see how much greater the light fastness is with the violet 19 over the other color indexes that are shown here. Continuing in some plastic applications, here's just a quick comparison of some red 122s and the gamma crystal violet 19s in a full tone type of a formulation, as well as a tint tone. So very good weather stability or accelerated weather stability for these types of chemistries. And then on the coating side, here is an example for the beta crystal violet 19 in a metallic type of a formulation because of its transparency. This is a typical application for that type of a system. And so here we're showing some 3 different levels of metallic in the formulation. And then from the pigment red 122 space, this particular series is still ongoing. But up until now, we see some nice results with respect to in this solvent-based automotive paint type of a formulation for accelerated weathering. As far as the quinacridones are part of our Sudarshan family of pigments, which denotes that it is part of the high performance pigment base in here. So you can get an idea of where the positioning is of these types of chemistries in our portfolios. From a color portfolio perspective, the red 122 and the violet 19s are ones that we've discussed today in this webinar. However, the other circled color indexes are other indexes that we have in our red shade portfolio. And then similarly for the violet shade, we discussed the beta crystal of the violet 19. And then we also have some other violets in our portfolio as well. And as I've always stated, I can't do this by myself, so I just like to give a shout out to Gorak for helping me prepare all this information for you today. And of course, the technical service support that we get from our labs in India, which is coordinated by Kunal. Our next series will shift back into azos, where we're going to take a look at our high performance azo pigments. That will be in May on the 25th. So we will so look for that invitation the week of May 17th. And in future series, I'm going to mix it up a little bit and talk about pigment finishing. In the June edition of this webinar series. So that should provide you a little better look into the impact of how a pigment is finished and how it impacts the end application. And we are also interested to hear what you are interested in. So one of the things that I'll add in my my note to everybody here is that you know, if there's something that you have an interest in, then we would like to hear that and put it into our series as well. Of course, you know, I'm not on an island by myself. We have a nice team here in North America that is here for you and your needs. So if you have any questions, feel free to reach out to any one of us, and we can help. So at this point, I'd like to open it up for any questions that you might have. And then we'll close the session for this month. So if you have any questions, you can use the chat box or just jump online.
Bonnie, hi, Basilio from IMCD here. Thanks for a great presentation. This is an area I'm a bit weak in, so this was really good for me. Couple of questions. On when you were discussing Pigment Red 206, you mentioned the QAQ colorant. I'm just wondering, is that QAQ, is that useful on its own at all as a colorant?
Not very. Primarily because the it has very poor light fastness. So even on interior type applications, it does have an issue with that particular property. So coloristically, it does have use there, but from a performance perspective, by itself, it's not useful.
Okay, thank you. And my second question was, when you were talking about the solid solutions, what would be the benefit or drawbacks of trying to accomplish the same thing, just doing say a dry blend of the two pigment types involved?
So what you are where the solid solution becomes important is it's not a dry blend. It's
Right.
bonding the two molecules together. So that creates a different dynamic with respect to dispersing the pigment in the end application. So if they're too different, then a good example, you just asked a question with the red 209 in there being the QAQ and the and there. So separately, you will get a poorer weather fastness and light fastness performance if they were blended separately versus the bonding together as a solid solution in there. So there's two reasons for the solid solution. As one is as far as from a technical performance, you don't get you either if you blended them separately, then you still carry through the technical properties into that blend versus the solid solution then overcoming them, as well as the dispersing properties of the individual ones. One might be very poor versus the other. So it makes the dispersibility very different as well versus coming together as a solid solution.
So that's my 2 cents on the solid solutions. For the drowning portion, what you're doing when you're in a process and manufacturing these, you have a synthesis or you have a reaction taking place. Drowning means you're adding some kind of chemicals or solvent to it to stop the reaction. And it's another way to say is quenching it, to basically you have a reaction that's going on. You add these series of chemicals, whether it be solvents, water, amines, it can be anything. And that stops the reaction because again, if you don't, a lot of the particles, you'll continue to see particle growth and things like that in the manufacturing process.
Thank you, Ron. Bonnie's back, but you're still muted. You're muted, Bonnie.
There you go. Sorry about that. Apparently my my internet's not that stable today. In there, so thanks, Ron, for that one. So there was another question about what aspects of quinacridones make them difficult to grind. Couple of areas there that might make them a little bit more difficult to grind is their hardness is more hard than say a classical pigment. In there, you can imagine with these very tight molecule, the cyclic molecules, they do generate those tighter, more complicated crystals, which gives them their lovely properties as well, but also can make them more difficult to grind. Their surface area tends to be greater because of that as well. So typically when you look at the surface area and oil absorption numbers of these types of pigments, they demand more dispersant usage to be able to get an adequate and useful grind out of it. Another one, can you share any improvements in sustainability in quinacridone manufacture or finishing steps that are possible in the future? Is this an area that can realistically be improvements? Okay, there's the $1 million question in there. So these are organic in nature, and so all of the raw materials that are going into these things are organic in nature. They come from the petroleum industries. So there are ways to use certain amounts of bio raw materials. This becomes difficult, as I mentioned, in that first the first step in the synthesis, where we are creating the DMSS. That then interferes with the yield output. So on the one hand, you're using biomaterials, but on the other hand, you are lessening the yield of that important ingredient to be able to create that chemistry. So it's not so.
There's maybe a couple of points you can mention here, which is not necessarily based on the chemistry, but one obviously will always be the wastewater treatment of how it's handled in our plant. On the front end, we are looking on the things where it obviously takes a lot of energy to manufacture pigments. So a lot of our sustainability part comes from using green energy. So we are installing windmills. We have solar power fields installed where we are basically pulling most of the energy from for our pigment manufacturing. Part of this, we still have our own coal power plant as well. At this point of time, this is still needed, as you also need to generate steam, which is needed during this production process. But wherever we can, we utilize our windmills and solar power for sustainability, at least energy sources in this part.
Correct. And that's where the also the difference in processes come into play, where the PPA process is at a much lower temperature than the thermal process and requires a lot less solvent in there. So there's those aspects of that goes towards that sustainability aspect of it. Question is, do you recommend solid solutions for magenta process color for printing? If so, which ones and why? For process colors, depends on, so that's a tough question. So it's not to say that solid solutions couldn't be used in printing. It really depends on the color space that you're trying to achieve. Solid solutions tend to be more unique in color than the traditional straight grinds. So I mean, so if you need that color space, then they certainly could be used. But knowing that the algorithms that go into printing colors, you can get there with your traditional process colors. And Ron added in, yes, certainly solid solutions are going to be more expensive than the traditional quinacridones, like a Pigment Red 122, for example. All right, is there any questions? Any more questions? Great. Well, thank you again for joining us today, and we look forward to seeing you next month when we talk about some high performance azo pigments. Hope everybody has a great day and enjoy, and we'll talk to you soon. Thanks again, everybody.
Thanks, Bonnie. Good job. Thank you.
Thank you, Bonnie. Thanks
Thank
all
you.
for
Thank you.
Thank you.
Thank you, Bonnie.
Sure thing.
Thank you.
Thanks, Bonnie.
Thanks, Bonnie. Bye-bye.